The last thing I'd like to show you is Johannes Itten's color star. This is something that he invented at the Bauhaus, and it's actually a kit for working with color relationships. Here on the cover, we see his color wheel, a slightly different form, where the pure colors are here. There's concentric circles of tints that move to the center, and then points of shades, all the way to black on the very outside tips. And you can imagine this now being cut out, and where all the points are gathered, you create a sphere. And that sphere becoming how we understand color, with lights at the top, darks at the bottom, and around the equator, the most vivid colors. When we open up this kit, we see a reproduction of the color star, the color wheel that was on the cover, with a little bit of a spindle in the center. And then there are a series of discs. And each of these discs can be placed on top of the spindle and moved around. And this is where it gets really interesting. So Itten thought of color and color combinations as chords, like musical chords, where colors, when put together, would have a harmonic relationship similar to musical notes going together and having a harmonic relationship. So this is what he would call a triadic color chord, a triad, 3 colors that work together, and they're the primary colors. And I can spin this around and see all of these different triadic color chords, and each one of them has its own sensation, its own personality. Just as if you were playing chords on a piano or on a guitar. If I take another disc, this one is a dyadic color chord, 2 notes, 2 colors. These are complementary colors, going back to that idea of complementary contrast, yellow and purple, orange and blue, red and green, and all the tertiary combination. Complementary colors are like go-to color palettes. They always work. There's always a sensation that exists in between them that's very specific. This is what's called the split complementary color chord. It's a triad, but a different kind of triad. Not the same where the openings are placed in an equilateral relationship. This is an isosceles triangle. And this is similar to the dyadic color chord, except instead of using the direct color opposite yellow, in this case, we split those 2 colors and use the analogous colors to the complement. So the complement would be purple, but here we have red-violet, or red-purple, and blue-violet, the 2 colors that are adjacent or analogous to the complement. This is one of the most useful color chords there is. And once you become tuned into this, you start to see this in a lot of people's work. Split complementary color chords. Very beautiful. So this is a great tool. And there are definite tools like this that are in use on the computer. Adobe has one that's very similar to this. It works with split complements and triads. This idea has been put into different kinds of color instruments for our use, and we can use it as a daily tool for helping us make color decisions. And we have Itten to thank. Now I'm going to talk a little bit about Itten's color ideas, color contrasts, and show you some examples on the computer. So we've already taken a look at Johannes Itten's The Art of Color, where he describes the 7 color contrasts using grids and examples of works of art. And now we're going to take a look at the 7 color contrasts again, just briefly in this presentation, and then do a little bit of experimentation with color grids, where we actually demonstrate the 7 color contrasts in a very simple way, using very simple forms, grids, where all the shapes are the same size, and all we're really dealing with is color interaction and color contrast. So stripping away all the other possibilities of representation, trying to make things look like other things. We're not making a landscape. We're not making pictures of any kind. We're just working with color. Now, the great thing about color grids, of course, is that it allows you to work with patterns. It allows you to experiment with the idea of symmetry and asymmetry, and also thinking about visual hierarchy. We'll get into it. So, Johannes Itten and the 7 color contrasts. The first color contrast is contrast of hue. And when we're talking about contrast of hue, we're really talking about the visible chromatic spectrum that we as human beings can see. And as we see here in this slide, the entire range of colors that we are aware of as humans is visible. And we can divide these colors into groups. And that's really the easiest way to understand contrast of hue and get a general sense of how we perceive color and how they relate to each other. So we'll talk about first the primary colors, red, blue, and yellow. And we see their relationship on the chromatic spectrum up here on the very top. And if we go down to the squares, we see them isolated. And the reason that they're called primary colors is because they can't be mixed. They are what they are. Red is red, blue is blue, yellow is yellow. And there's no 2 other colors that you can mix in order to make yellow or blue or red. So we call them primary colors. The secondary colors are mixtures of the primary colors, and they're in the second row. So purple is the mixture of red and blue. Green is the mixture of blue and yellow. And orange is the mixture of red and yellow. And then the third row at the bottom are the tertiary or in-between colors. And these are all mixtures of primaries and secondaries. So when we mix red as a primary with purple, the secondary, we get red-violet, sometimes called magenta. It's a tertiary color. When we mix purple with blue, we get blue-violet or navy. Blue and green, we get blue-green, sometimes called turquoise or aqua. Green and yellow, we get yellow-green, sort of the color of a lime. Yellow and orange, we get yellow-orange. And then orange and red, and we get a red-orange, a warm red. So that's contrast of hue. Very simple idea. If you can memorize this concept of primaries, secondaries, and tertiaries, and visualize how they're related to each other, then you'll always have a sense of how color is related in a systematic way. Moving on to the second color contrast, contrast of value. So here we're dealing with light and dark, as if you're adding black or white to a color. So in the first row at the top, we have a typical grayscale broken into 12 units. And the reason that we break these into 12 units with a grayscale is because as humans, our eyes have a difficult time seeing differences after a certain point. And we found that 12 separations of the grayscale is just about enough for us as human beings to clearly see differences. And as we look at this grayscale, we can see that each of these grays is distinct. So when we move down to the second row of yellow mixed with white and black, the purest yellow is very close to the lightest, so over here. And as we move toward white, we see very few tints. And lighter variants of colors are called tints. Darker variants, colors that are, when they're mixed with black, are called shades. So tints and shades, and that's a good terminology to always remember. A tint is a pure color mixed with white. A shade is a pure color mixed with black. So yellow, very close to white in its value, very light, has very few tints, but many shades. It takes a long time to get to black if you're mixing small amounts of black with yellow. We go down to the third row, we have purple. Purple is just the opposite of yellow. It's the color that is closest to black in value. And as we see, probably the purest purple is way, way, way down here on the right side, very close to black. A lot of tints, So purple has many, many tints, the opposite of yellow. It takes a long time to get from a pure purple all the way to white. But purple is also very close to black, so it has very few shades. So all hues, yellow, orange, red, purple, blue, green, they all have relationships to black and white, and they're called light values. When we talk about contrast of value, we're really talking about that, the relative lightness or darkness of a color. Saturation, a little bit different. Here, you're taking a pure color and you're mixing it with, rather than black and white, mixing it with gray. In reality, anytime you mix a pure color with something else, another color, even black and white, its complement, its opposite, you're always desaturating. Saturation is really the identity of the color. So a fully saturated color is fully identifiable. It's the color we think of most prominently when we think of, say, the name of a color. When we say red, we're thinking of a very pure red, most of the time. Same thing with yellow, same thing with blue, same thing with all the primaries and the secondaries, and even the tertiary colors. When we say yellow-green, an image comes into our mind that's very specific. So as that identity goes away through the mixing process, either by mixing it with gray or mixing with its complement, talk about a little bit later, you desaturate. And eventually, all of the identity of the color goes away. So as we look at these chromatic scales, we see magenta or red-violet here right in the center in the top row. And as we move toward either end, there's a gradual mixing that happens between that color, that pure color, and gray. And as you can see what happens down here, when we're very, very close to the pure grays, which are on the very ends, colors that are next to them are called chromatic grays. They're these beautiful grays that have notes or tints, very small amounts of the parent color. So this gray right here has a very small amount of the magenta. Go down to the second row where we have orange, pure orange in the middle. And as we move to the outsides, that pure orange becomes desaturated. It loses its identity. And then we see these beautiful chromatic grays that are the second steps in from the ends. There we have sort of a warm gray, very different than the gray that's made from mixing with purple or violet or magenta. And if we go down to the very bottom row where we have this blue-violet, we mix that with gray. Again, you move from the center to the outside edges, gradual mixtures with gray, right down to this point here where it's right on the end. There's absolutely no chromatic effect. It's pure gray. And then we have the chromatic grays right next to it, here and here and here. Really beautiful. That's saturation. So the easy thing to remember is saturation has to do with the identity of the color. As soon as the identity becomes confusing or unclear, as soon as you lose the idea of the color, the identity of the color, it becomes less saturated. Complementary contrast. So when we mix two colors together that are on opposite sides of the color wheel, like green and red, blue and orange, purple and yellow, these are all colors that are opposite to each other on a color wheel. You can look at almost any color wheel, not an RGB color wheel, because that's a different formulation, but a CMYK color wheel or a painter's color wheel, a traditional color wheel, and we can see this. We can see how these colors are opposite to each other. And that means that in order to get from one to the other, you go all the way around, halfway around the color wheel in order to get there. So they're as far away as possible in terms of hue. Red and green are complements, blue and orange are complements, purple and yellow are complements, yellow-orange and blue-violet are complements, yellow-green and magenta are complements. So try to visualize the color wheel and see the relationships of the opposite colors. When you mix complementary colors together, you produce a chromatic gray, and that's another form of desaturation. So as we look at these rows, the purest colors are on the ends. Those are the parents. Those are the complements, right? Red and green. And as you move toward the center, on the red side, you get gradually less red until we get right to the middle, right into the middle area here, where the color has almost lost all of its identity. There's still a little bit of a chromatic effect, but it's very difficult to say what the parents are at this point. And as we move toward green, we gradually build back up to the point where the green is fully saturated on the ends. Go down to the second row, we have orange and blue. Again, you move in from the outside edges, you move in from the blue, you move in from the orange to the center. In the center area is the chromatic grays, the mixtures of those two complements. Same thing with purple. As we move from the outsides, the pure yellow, pure purple or violet, we move to the center, we become less and less saturated. You get to this perfect sort of beautiful chromatic gray in the center. Now, the true test of whether colors are truly complementary is if you can produce a perfectly neutral gray. And it's really hard to do, but it's a really interesting idea. And maybe we'll try that when we get to our color grids and we do a little bit of color mixing. Contrast of temperature. So far we have contrast of hue, contrast of value, contrast of saturation, complementary contrast, now contrast of temperature. Contrast of temperature is all about the sensation of warm and cool that colors seem to emit or suggest. And in some cases, there's a physical sensation of temperature change. If you are in a room that's fully painted with a warm color like red, your body temperature will increase very slightly. Same thing with a cool color. If you're in a room that's painted blue or blue-green, your body temperature is going to sink a little bit, get a little bit cooler, again, almost imperceptible, but measurable. So warm and cool colors are associated with warm and cool ideas, fire and water. Now think about how long those ideas have been part of human culture and just our way of thinking and dealing with the world. Every night we see a sunset that's produced by the complements of blue and orange, which are also the warmest and the coolest colors. So we're very used to seeing that idea. We're also used to seeing fire, which is red or yellow or orange. And we're used to seeing the reflection of the sky and water, which is often blue. So we associate those ideas of water and fire, cool and warm, with those colors. So it can be very conceptual, but it can also be a really good idea just to, say, create contrasts of color, warm and cool contrasts. Certain hues can be warm or cool, not all of them. So a red can be warm, like orange, or red-orange, or cool, like red-violet. A blue can be slightly warmed up by moving toward green. It's a little bit more difficult, but possible. Green actually can be warmed up or cooled down by moving toward blue or moving toward yellow. So you can experiment with this. Look at one hue and look at the two analogous or adjacent colors on either side of that hue and say, how can we warm up or cool down this color? It's just another way of thinking about color contrast. Contrast of extension has to do with the proportions of colors used in different amounts together. So when we think about proportions, we're always saying, okay, how much yellow versus how much purple, or how much blue versus how much orange, how much red versus how much green. When we're looking at Itten's book, contrast of extension is so much about that idea of proportion and getting those proportions correct in order to create harmony. So 1 part yellow, 3 parts violet will create a sense of harmony. 1 part orange, 2 parts blue will create a sense of harmony. 1 part green, 1 part red will create a sense of harmony or stasis. As soon as you change those proportions, other forces come into play. So if we have more than 1 part yellow, all of a sudden it becomes so dominant. If you have a composition where you have 3 parts yellow and 2 parts purple, the yellow will certainly dominate. And this is something, again, to experiment with just on your own. This is a little bit subjective, but it also is relatively mathematical. Again, you remember those proportions. 1 to 3 for yellow and purple, 1 to 2 for orange and blue, and 1 to 1 for red and green.